Okay, so in the first example, we learned how to put in the stiffness matrix, the piezoelectric matrix and the permittivity of the material, and we learned the converse piezoelectric effect because we applied an electric field in the polarization direction, and we then looked at the corresponding strain. So in this case, we're going to use the direct piezoelectric effect and look at a voltage that's generated under applied load. So what I'm going to do is just resume from inputting the materials properties because we did that in the previous example. So I'll just load in the properties just to quickly recap. So I've got a solid 5 element, which is that coupled field element. I have my materials properties, materials models. I've got linear elastic stiffness matrix. So I've got my stiffness matrix of PZT5H. I should have my relative permittivity here, which is orthotropic, so X, Y, and Z, where Z is the poling direction, and then I should also have the piezoelectric matrix. Good. So I'm going to do the same thing again and just create a nice block because create a volume as a block by dimensions, 1 meter by 1 meter by 1 meter. I know it's a bit strange, but it just makes the analytical solution a lot simpler to calculate. So I've got a 1 meter by 1 meter block. Let's just mesh that. So we mesh our block, use the mesh tool, smart size, nothing fancy, mesh. Pick all. It's warning me here that I should have an element with mid nodes, but this is a very simple shape, so I shouldn't really have any significant errors. So solid 98 is a tetrahedron that may be more applicable for more complex shapes. So remember, I now need to add some electrodes on the top and bottom in the poling direction. So let's look in the let's just get a nice, there's the Z direction. So I'm going to put an electrode at the bottom, electrode at the top. So select entities by our nodes as a box. So couple set 1 will be the electrode at the bottom. And so I couple those, CP 1 volt all. So in the degree of freedom volt, these are all coupled. Plot, replot. So remember, I've only selected, so I need to select everything just to reselect everything. Plot, replot. And now I select the top nodes as a box. So when you write code, you can do it by position. It's a lot easier. OK. And then couple set 2 in the degree of freedom volt. All. Select everything, plot, replot. So here are my 2 electrodes on the top and bottom. And now let's just plot areas here and maybe just fit that. Where's that? Let's fit that to the model. So what I want to do now is apply a downward pressure to generate a voltage. So I'm going to apply a pressure on this surface. I'm going to apply symmetry on these 3 surfaces, these areas, to represent almost a part of a larger cube in the material. And then I'm going to set this low electrode to 0 volts. So basically earth that electrode. And then I'm going to let this electrode at the top float. I'm not going to give it any value at all. So when I press down, should develop some charge. That charge then will lead to a potential difference because it's open circuit. There's no charge flowing away. I should then generate a voltage on the top. So let's go to solution. So it's a static analysis. Let's define the loads. So let's do the boundary condition first. The symmetry. So I put symmetry on these 3 faces. So apply structural displacement symmetry on the areas. So this area, and this area. So I've got symmetry on those faces. And then now I'm going to apply a downward pressure on this face. So I'm going to apply a pressure on areas, pick that area, okay, and a pressure of 1 newtons per meter squared, 1 Pascal. That's good. And then if I just look at my couple set list, just to remind me, so my electrodes 1 and 2. So couple set 1 has these nodes, and the first one is the master node. So number 1 is the master node, and all the others will follow. On couple set 2, number 17 is the master node, and all the others on that list will follow. So 1 and 17 may be worth remembering. So I'm going to set this to 0 volts. So I just need to set number 1 to 0 volts, and all the others will follow. So I'll apply a potential on nodes. Just select node 1 and ground that, so 0 volts. There it is there in yellow. That's good. So I've got symmetry on these 3 faces. I'm squashing down on this face. Let's just zoom out a little. Squashing down on this face. This will be ground, and the voltage will be developed on the top face due to the charge that's being generated. That's fine. I tried this earlier, and what I didn't do is apply some convergent tolerance controls, and I've learned that helps get a quicker solution. So it's convergent tolerances in force, and we just know from experience, setting it to a small value for convergence of force 1e to the minus 6, and the same convergent tolerance for amps, and 2, 3, 4, 1e to the minus 6, and convergent tolerance volts, 1, 2, 3, 4 commas, 1e to the minus 6. That helps with the solution. So, okay, so I've got my symmetry, got my 0 volts at the base, and my pressure. So let's solve current load set, see if this works. So 2 warnings, and that's because I've got magnetic and temperature components in my elements, and I haven't really set any, but I don't need it. And solution is done. That's fine. It took a little bit longer without those tolerance before, so I should now be able to look at my results. So let's just look at the deformed shape. Yeah, so I've squashed it down, so I've got a deformation in the material. Maybe just out of interest, let's look at the displacement in Z. So just out of interest here, I've got 0.91 e to the minus 11 meters displacement. Let me just write that down. So it's 9.1 times 10 to the minus 12 meters. So that displacement due to a 1 Pascal, because that's linked to the stiffness of the material. And the other obviously important thing that we're really looking for is the electric potential. Here I've got my 0 volts at the base, and I've got a voltage, so it's a negative voltage. So I've got 0.0195 volts. That's being generated. And I think if I do read results, I think I have to say read the first set. I think I can always also look at the electric field. So if you scroll down here, because I've got a potential difference, electric field, and it'll be in Z in the poling direction. So I've got an electric field across it as well. I think you can also do a vector plot of electric field. looks nice. Not sure if it gives us anything more. Flux and gradient, electric field as well. Yeah, so I've got an electric field, you can see, that's going along that poling direction, and I've got a value, and because T is 1 meter and thickness is 1 meter, that's the same as the voltage as well. So that's good. So that's fine. So let's maybe see if it's the right value, 0.0195 volts. So I've got a PowerPoint slide here. PowerPoint slide here. So if I just scroll back, so I've got a pressure of 1 Pascal on my piezoelectric 1 by 1 by 1 meter block. I've got 0 volts here. I've got a floating voltage here, so it's open circuit. So my charge is D33 times F, and that's the charge per unit force, so that's the piezoelectric coefficient. I know the capacitance of this, it's like a little capacitor in a way, is area times permittivity of the material divided by thickness. This is permittivity times the permittivity of free space, if this is the relative permittivity. And so my open circuit voltage, I just, from Q is equal to CV, my open circuit voltage is basically sort of the charge, which is D33 times F, divided by the capacitance. So it's 1 times 1 over C. So here I've got my permittivity, my stress, in a way, because it's F over A times T. So my stress is 1 Pascal. So this is 1. My thickness is 1. So really, my open circuit voltage should be D33 divided by the relative permittivity times the permittivity of free space. And when I pop that in, I get 0.0197 volts. And what did I get? 0.0195 volts. So that's pretty good. That's pretty good. I also measured the displacement, and you can check this. This is just Hooke's law. Stress is equal to stiffness times strain. This is open circuit voltage, remember, and so that's related to the compliance under this constant dielectric displacement D, and I get, and because the stress is 1 and the thickness 1, it's just 1 over E, so it's just the same value of S333D. So I get 10.4 times 10 to the minus 12. I think I got something like 9.1 times 10 to the minus 12. So not exactly the same. And that might be because I got this value here from the literature somewhere else. And that I might actually be putting in a slightly different value of S33D by putting in the compliance, the stiffness matrix that I've put in. And maybe there's subtle differences between the values from the paper I've just got this from and also the value that I've put in the literature, but it's pretty close, and that's pretty good. But certainly this has worked, so it's given me confidence that it's doing the right thing. So that's good. It's worked out nicely. We can do another quick test because I can just take my existing model. I never really do this in a way. I always like to start from scratch. But if I plot my nodes again, so remember at the bottom, so let's just plot the area, maybe it's easier. Remember at the bottom I had 0 volts, and the top I had floating, and that was open circuit, and it was settle. So if I imagine now a situation where I short circuit my model, so what I'm going to do now is set the top at 0 volts as well. So I know from my capital list set that the top master node is what, 17. So if I apply in my define the loads, so if I apply an electric boundary on nodes on the top electrodes, so 17 was that master node in capital set 2. If I make that at 0 volts as well, yeah, I've got that yellow here. This is 0 volts. The bottom is 0 volts, and I've still got a pressure. And because they're both at 0 volts, I shouldn't develop a voltage difference now. And what I should do is really develop a charge that corresponds to discharging this material. So it's now under short circuit conditions. So let's solve that. So I've still got all my other convergent tolerance and conditions, so I've solved it. It's fine, it's good, it's done, no errors. So if I look at the general post plot the results, I always like to do deformed and undeformed shape first. So something's happened. So let's look at the displacement. So my displacement in Z. Oh, so that's interesting. So that displacement now is 20.8 times 10 to the minus 12 meters. That's fine, that's good. So that's 20.8 times 10 to the minus 12 meters. And now if I look at the voltage, I shouldn't have anything. So yeah, so I've got a tiny one, e to the minus 17. So I've got no real potential difference across the sample, and that's because it's under short circuit. So really I want to try and look at the charge, and it took me a long time to find this. Where's the charge? So it's in general post-POC. Can I find it? Oh, reaction low. So so it's in list results. Reaction solution. So it's the reaction. So it's not you can't really plot it as a curve because it's just a number. So if you look at reaction solution, what you need to do is the corresponding charge that's generated. Now again, this is an artifact of ANSYS. It says amps here, but there's no real current because that's got a time element. That's sort of dq dt. But if you click on electric current, that actually provides the charge that's generated to maintain that constant 0 volts. If I click on that, I get 594 times 10 to the minus 12 coulombs. So remember that number, and we'll see what happens. So let's look at my PowerPoint. If we look at slide 2 now, so this is closed circuit condition, same condition, 1 Pascal, bottom electrode at 0 volts, top electrode now at 0 volts. So it's short circuit. So my Q charge is D33 times F, and D33 is 594 picocoulombs per Newton. F is 1 Newton, so I should have 594 picocoulombs, and that's exactly what I've got. I've got 594 picocoulombs as that reaction solution. So that's perfect, and that's needed to maintain that 0 volts. And if I look at the deflection, again Hooke's law, stress is stiffness times strain, and strain is delta T over T. So the sigma, the stress is 1, the thickness is 1, so basically delta T is 1 over E, and that's equal therefore to the compliance at constant field now. So this is the compliance at constant field. So it's a different value of stiffness because it's depending on the boundary condition. And that value that I have for PZT5H is 20.8 picometers, and that's exactly what I get in the model. I've just written it down as we went through. So I get the same deflection as I get in the model. So that's really, really nice. And the point to note is it's deflecting more in closed circuit than in open circuit. So it's about a factor of 2 compared to open circuit. And that's because as you're compressing it under open circuit, you're getting a Hookean strain, but also you're developing an electric field. We saw it. And what does the piezo do under that electric field? It strains, and so it recovers some of that Hookean deformation due to the piezoelectric effect. And so it's stiffer under open circuit compared to closed circuit. And here in this case it's a factor of 2. Yeah, so it's twice as stiff under open circuit compared to closed circuit, so you get half the deflection. And surprise, surprise, how do you define the efficiency? It's almost defined by the coupling coefficient, and that coupling coefficient K is very much related to the stiffness under open and short circuit conditions, and the efficiency is about 50%, and that gives rise therefore to this deformation. Good.